Well, good evening, everyone. I'm David James, and it's my pleasure to welcome you to this Institution of Engineering and Technology Sussex Network talk. Okay, well, it's my great pleasure to introduce David Stoddart. David is head of the Simulation and Verification Group at the Nuclear AMRC. That's the Nuclear Advanced Manufacturing Research Centre. The group helps manufacturers improve their productivity and quality and explore new digital technologies. They offer multidisciplinary support to model, measure, analyze, and optimize production, from overall factory layout to individual manufacturing processes. David led the Nuclear AMRC contribution to phase 1 of the UK SMR programme. That's a Small Modular Reactor programme. David joined the Nuclear AMRC in 2011, having previously been a senior mechanical design engineer for Sellafield, where he worked on the design for a number of intermediate level waste treatment plants. He graduated with a master's in mechanical engineering from Cardiff University in 2003 and achieved chartered status with the IMechE in 2007. Now, it seems that David's passion for engineering was inspired by his grandfather, who was a long-serving member of the South Wales branch of the IET. Now, what better recommendation could we have than that? So it's my pleasure to hand over to David. I'll stop sharing my screen and we'll let David share his. So over to you, David.
Thank you very much. Let me know when you can see the screen and it's in presentation mode. It's not put into presentation mode just yet, is it? Okay.
Yes, now we can see it.
Okay. Perfect. Yeah. So thank you very much for that very kind introduction, and thank you for inviting me along this evening. This is a quick overview of the sort of topics I'm going to touch on, and I'll give a quick introduction to the Nuclear AMRC and the reason for we exist and the sort of things we do there. When I originally put the agenda together, I sort of was about to jump into the advantages of SMRs over more traditional reactors, but I thought with it being such a varied audience, it's worth pausing for 30 seconds or so on why I personally believe that there's a case for any sort of nuclear power in the UK. Then I'll talk a little bit about the opportunities for SMRs, particularly SMRs to be built and deployed in the UK. And then I'll go through a range of case studies of some of the advanced manufacturing development programs we run at the Nuclear AMRC. Now, these have been designed and funded partly by the Nuclear AMRC themselves and by government funding, and they are not tied to any particular SMR technology. They are designed to be technology agnostic, really, and they will have benefits that are applicable to multiple technologies, components, geometries. And what we will be doing is sort of putting the results of these in front of various vendors and manufacturers, and hopefully deploying them across a range of key stakeholders. And I'll finish with a couple of key thoughts, a sort of follow on from the earlier topics in there. And then there'll be some time for some questions. I've probably tried to cover too many topics in the presentation, so I'll be a little bit light on detail as I go through. Hopefully I'll be able to give a bit more explanation in some of the answers. If I don't know the answer, I'll take it away and then come back to David later with further thoughts on the particular questions, or it may be that there's commercial sensitivities and I can't answer the question. So if that is the case, I'll try and make it clear. So the Nuclear AMRC, the Nuclear Advanced Manufacturing Research Centre, it's part of the University of Sheffield, but we're a standalone facility on the outskirts of Sheffield, at the Sheffield-Rotherham border. And very simply, our mission is to help UK companies win work in nuclear and other high-value manufacturing sectors. So in the image there's an example of one of our machines. In a moment, I'll talk about some similar centres, but essentially, we were set up to support the nuclear industry, but we will also support industries whereby their manufacturing challenges are at large scale. So We're particularly focused on nuclear new build operations, decommissioning, advanced technologies and propulsion, and then some of the other industries that we touch upon are renewable energy, a little bit on oil and gas, but that's very small these days, marine, aerospace, chemicals, and big science. And by big science, I mean supporting endeavors like CERN in Switzerland or large-scale experiments where the sort of components are large and accuracies are quite challenging to achieve. And essentially, to sort of achieve that mission, we sort of go about it in two business areas, if you like. There's the manufacturing innovation side of the organization, which is the area in which I work, and the case studies that I come on to at the end of the talk will be based in that. And in that, we're looking to improve cycle time of component manufacturing, reducing lead time, cost, and risk, and developing innovative techniques and technologies for the manufacture of these components, and then working with our partners and customers in order to deploy them in their facilities, and so to ensure that the innovation that we come up with in our facility is the values of that are realized in the UK supply chain, and we do work internationally with international partners as well. And then there's the supply chain development side of the business. So this is we have a range of sort of business excellence programs in that side of the organization, where we will work with companies who are either about to enter the nuclear supply chain or believe that they have capabilities and resources that are suitable for the nuclear industry. We'll go in, we'll sort of assess their what they make, is it suitable for the nuclear industry, but it's mainly around sort of safety culture, quality culture, business excellence type KPIs and metrics that we measure on them, and then we sort of put in some assistance to ensure that they are then fully fit and ready to enter the supply chain for the nuclear industry. So we're part of the Advanced Manufacturing Park out in Rotherham. I'm not sure if you can see my cursor on the screen, but if you can, that's the nuclear AMRC there. It's got 8,000 square meters facility. We are owned by the University of Sheffield, and at this park as well, we have our sister organisation next door, which is the AMRC with Bowen. Over here, we have the AMRC training school, where we train 200 apprentices from across Yorkshire and wider every year in a range of disciplines. And on the site, we've also got people like Rolls-Royce. This is one of their turbine blade casting facilities, and we've got just off shot, we've got McLaren have joined the park to manufacture monocoque chassis, carbon fiber chassis for the high-end cars. So it's quite a exciting place to work and to be based. And this is what it used to look like. So we like to put this slide at the beginning of our talks, depending on who we're presenting to and who the stakeholders are, because it's the area and the region is a good example of how sites that are sort of post-industrial rundown can be regenerated with a bit of government support and some innovative ideas. So the original concept for the AMRC came from basically a manufacturing technology idea from one professor at the University of Sheffield. He managed to convince a local company who made tools that there was mileage in this, and that they developed a new metal cutting technique that they were able to convince Bowen was a good idea. And from that initial project, they were able to convert the image on the right into the image on the left with government support and a lot of sort of hard work from some innovative people, in fairness. So if you ever see old footage of the miners' strike and policemen on horses attacking striking miners, that happened just about there, just that side of the road on our facility. And the nuclear AMRC is part of a wider network backed by the UK government. So there are 7 centres that form part of what is called the High Value Manufacturing Catapult. So we have the AFRC, which is the Advanced Forming Research Centre, based up in Strathclyde, the Centre for Process Innovation up in the northeast in Middlesbrough. Then there's the Nuclear AMRC and the AMRC on the Rotherham facility. The Manufacturing Technology Centre and Warwick Manufacturing Group in Coventry. Excuse me, and the National Composite Centre in Bristol. So we don't have great coverage in the southeast at the moment, or in Wales, but in the southwest, we work with various partners such as NPL in Teddington, and a few of the universities in London who are very strong on manufacturing. And so the reason we came into being really, or the high value manufacturing catapults came into being really, was to help plug what we call the innovation gap. So that scale there is the manufacturing readiness level. You may be familiar with this, and you may be familiar with the technology readiness level, but I'll just go through it. So typically, university research looks at manufacturing readiness levels 1 to 3. So that's lab-based prototypes and PhD funded research. And for a long time, the UK has had a reputation for really sort of world leading PhD level research output, with a sort of very high impact PhDs, very high impact research papers being published from a lot of universities. At the other end of the scale, 7, 8, 9, that's essentially implementing new technologies into a business and then optimizing them up to 9. And there are pockets of really good performance in that area in the UK. People like Rolls-Royce are sort of, again, world leading at developing their processes to optimize them, to get the absolute most out of them. But it was sort of noted that there was a gap in the middle. Not enough of the ideas at the sort of MRL 3 were progressing through this middle section up to 7. And essentially, the reason that is as you move from a sort of lab-based prototype through the sort of process maturation of the manufacturing technology, it becomes more and more expensive at each stage, and it becomes more and more costly at each stage, and with associated risk. So in order to achieve 6, for instance, you have to be making components that are basically at least 2/3 the size of the real component, and you have to be using processes that are production ready. So that's quite expensive research and quite risky research, being some of the reasons that ideas fall in that area. So we work with the University of Sheffield and other universities in sort of cherry picking what we feel are the really, or the most applicable ideas that they're coming up with for industry, and we work with industrial partners at this end to help pull them through. So the case for nuclear power in the UK then. So as I'm sure we all know, the UK has committed to being net zero by 2050. And just in the last couple of weeks, actually, a paper has been published, sort of confirming that nuclear is the joint lowest CO2 emitter per kilowatt hour of energy production. So in terms of the through life CO2 production of nuclear power, it's about 12 grams per kilowatt hour, which is essentially the same as wind power. And the vast majority of that CO2 is generated in the manufacture of the plant, the construction of the plant, and then the decommissioning of the plant. The actual nuclear process itself doesn't generate any CO2. So the more efficient you can build the plant, and the longer you can run it, the more, even more less carbon intensive, if you like, that the nuclear process is. There's the opportunity for, well, energy security. I mean, the demand for power is obviously going to continue to rise. We are reliant in some areas on importing some electricity, and there are some scenarios that would point to us importing far more electricity over the next sort of couple of decades. And nuclear energy, alongside the growth in renewables, offers us the opportunity potentially to minimize it, or if not eliminate that. Alongside that is economic growth. Now, the nuclear AMRC, and with continued government support, we believe that there's a real opportunity to manufacture a lot of the new nuclear plants within the UK, building new nuclear supply chains to service firstly the UK demand for nuclear power, and then as an export opportunity across Europe and the world potentially. And we believe it is sort of a reliable and proven technology. You know, we've had commercial nuclear power in the UK since the 50s. It's got an exceptional safety record. We do hear challenges around the sort of safety and the production of nuclear waste, but the modern reactors have largely certainly addressed the waste issue largely, and again, a number of initiatives to sort of drive that to even better levels. And we certainly wouldn't see nuclear as a competitor to other technologies. We believe that there needs to be growth in renewables and all others, but things like energy storage and carbon capture, whilst showing fantastic promise and will almost certainly be a part of the long-term net zero solution, they are currently unproven at large scale. I just wanted to sort of put this here just to illustrate that point a little bit. So this is a snapshot I took off from the Nuclear Grid website on Thursday morning. On that link there, you visit that site at any time, and it tells you sort of more or less in real time how energy is being generated in the UK. So at that particular moment, the demand was nearly 42 gigawatts. Over 50% of that was being generated by fossil fuels at the time. I think nearly 30% in renewables, which is fantastic. Obviously, 20% of that has been wind. So I can't remember what the weather conditions were like that day, but that 30% is highly dependent on the right conditions being in place. So at the time, nuclear was producing 12% of the demand. Nuclear at the moment, the capacity is about 15% of the UK generation, and all of that will be offline by about 2035. So firstly, we need to try and replace that capacity, that sort of 15% capacity. We need to completely remove the reliance on fossil fuels, or minimize it as absolutely far as possible to meet current demand levels. But obviously then when you factor in the electrification of transport, energy, heating, there are some predictions that say demand for electricity generation in the UK will sort of double by the time 2050 comes around. So there is a need for fairly major national infrastructure programs in order to meet that demand in a low carbon way. So current capacity then, so these numbers I think are actually slightly out of date now, because over the summer Dungeness came offline, and just recently one of the reactors at Hunterston came offline. But more or less we have a generating capacity of 9 gigawatts electricity today. And those industry companies put about £600 million per annum of work into the supply chain in the UK. And all of that power will be offline by 2035 under current plans. Most of them have had life extensions already, so I do believe that most of that will be offline over that time frame. Again, so the various papers have been published on what we actually need. So one estimate, I think this came from the Nuclear Industry Association. I've lost the reference somewhere, but yeah, but they're estimating that the UK will need 40 gigawatts of nuclear electricity by 2050. So currently there's 19 gigawatts planned for what we call gigawatt size reactors, so very similar to what's being built at Hinkley Point C. That's the only one under construction at the moment, where they're constructed 2 reactors to generate, as it says there, 3.6. Sizewell C and Bradwell B are still awaiting final permission to start construction. I think they are more or less there now, and I expect to see construction happening on those sites. And then potentially to supplement that, there are a number of smaller capacity reactors under development for deployment in the 2030s. So why do we need small modular reactors? Why not just build more of the very big ones, I guess? So there are a number of small modular reactors, and I'll show some images of some of them on the next screen. But basically, as the name suggests, they are a lot smaller than the Hinkley Point Hinkley Point reactor, and they come in a range of sizes. So they should be quicker to construct, which means that they start giving a return on investment sooner. They are broadly designed to be manufactured and assembled as much offsite in factory settings as possible. So that increases the certainty in the delivery it decreases the lead time to get those components to site, and it increases the level of quality in those components. In the UK, the sort of big players are UK SMR. Westinghouse have got a design, NuScale. There's a Chinese reactor that they're looking to deploy, and Moltex Energy, which is a molten salt type reactor. So in total, there are around 50 Generation 3 and Generation 4 designs. So Generation 3 are the same level of technology as being built at Hinkley Point C, pressurized water reactors. Generation 4 are reactors that are based on advanced fuels, so molten salt, very high temperature reactors. And they have a range of outputs from the smallest being 4 megawatts electricity, which essentially could be used as almost like a battery to power an industrial site or a small town or village in a remote area, up to 500 megawatts. So for instance, the Rolls-Royce one is about 470. The International Atomic Energy actually define small modular reactors as things being under 300 megawatts, but the people who design and build them still like to use the terminology small modular reactor. A lot of them are focused on cogeneration, so using the heat from the process to heat districts or industrial processes, and a lot of them are designed to actually form or generate clean hydrogen. And factory construction. So from my perspective, working in manufacturing, research and development, this is the bit that's critical. So typically the reactor at Hinkley Point C has been designed to be constructed. Small modular reactors are typically designed to be manufactured and assembled. So that's the key issue. And in them being sort of assembled and manufactured more in factory settings, we are able to deploy more advanced technologies and techniques upon them in order to get them manufactured in the shortest lead time possible. So the UK SMR, or the Rolls-Royce SMR as it is now known, it's a compact modular design, 440 megawatts. It's a Gen 3 pressurized water reactor. So the approach Rolls-Royce have taken to this is they have chosen a proven reactor technology. We know pressurized water reactors will work. We know that they'll pass regulatory assessment, and we know that they're reliable and efficient. What Rolls-Royce are now going to do is invest heavily in optimizing the manufacture, assembly and construction of this plant to sort of ruthlessly drive out any cost or waste or risk in any of those stages. So they are they are now in the process of recruiting very heavily across all of those teams, and they're going to bring to bear their sort of generations of sort of manufacturing process development onto this to ensure that it is built and constructed in as absolutely as lean a method as possible. They've currently got a target cost of about £1.6 billion per plant, and that will equate to a strike price equivalent of about between £40 and £60 megawatts per hour. And that range makes it competitive essentially with the sort of price for wind electricity generation as it is currently. There are the numbers that are going to be built in the UK go up and down, sort of depending on various scenarios, various sort of investment scenarios from government and demand scenarios, but they're sort of basing their initial program around the opportunity to build 16 in the UK, which would equate to about 40,000 jobs in the UK in the sort of design, manufacture, assembly and operation of these plants. And that sort of gives sort of £52 billion worth of economic value in terms of the UK market. And they are in multiple conversations with governments, investors across the globe. So there is definitely the opportunity for significant export benefits as well from this technology. So the phase 1 of the program concluded in the summer. In phase 1, it was a a consortium of organisations, so Assystem, Atkins, BAM, Nuttall, Jacobs, Laing O'Rourke, National Nuclear Laboratory, ourselves, Rolls-Royce, obviously leading the consortium, and TWI. Phase 1 was essentially a £36 million programme, partially funded by government, with match funding from that consortium, and that was to sort of develop the concept of the plant and to develop a baseline method of manufacture and construction. Within that, the nuclear AMRC's role was to look at certain technologies within the baseline method of manufacture, and then look at for advanced techniques to see how we could further improve the baseline. And we had a focus on those areas. So portable machining. So you can, even though this is a small reactor, we're still talking about large components. So when you're manufacturing large components, the machine tools and welding bays that you need to put them on are commensurately large and therefore expensive, and a long lead time in purchasing and installing them. So we looked at various methods for bringing smaller machines to the component, leaving the component in situ and then using small portable machines. Large scale metrology, so advanced techniques. A lot of things that people in the aerospace will be familiar for many years, and that and Rolls-Royce themselves in the aerospace are familiar with. So we're looking at really bringing over inspection techniques from aerospace and other high-end, sort of challenging tolerance industries into the nuclear industry. Component handling, looking at the most efficient and safe ways of moving large components around an optimized factory. And then digital twinning and module demonstrator. What sort of digital tools can we bring to bear to optimize the manufacturing planning and to de-risk investment in the sort of in developing the manufacturing process. Okay, so moving on to some of the case studies and technology development programs that we have run and are running, that, like I say, are applicable to multiple SMRs. The Rolls-Royce SMR is very close to our heart and will be, but these are independent of the Rolls-Royce program at the moment, with the potential for them to merge later on should these bear the sort of potential gains we believe that they're capable of. So this particular one is looking at pressure vessel manufacture. We set ourselves the challenge of reducing the production time for a reactor pressure vessel from what is currently about 2.5 years to less than 12 months. This was a collaboration with the Electric Power Research Institute, EPRI, in the United States. It's based around a 2/3 scale pressure vessel, an upper and lower assembly, as shown there in the image, and we deployed multiple technologies to try and bring down that lead time. And I'm going to touch on a couple of those now. So firstly, electron beam welding. So the process of electron beam welding, essentially you generate through a cathode and anode, you generate a high-powered electron beam that is focused through these lenses inside the machine. You use these to target it to the area you exactly need it, and then it hits the sort of workpiece. You don't use any filler wire, so you are purely melting the two components together. So you get, compared to arc welding, you get various benefits in terms of reduced heat affected zone. That image shows 200, but with we are able to go up to about 350 millimeters thick stainless steel, or carbon steel, sorry, 508 is the one we typically weld with this, but we are able to do about 300 to 350 millimeters welded section in a single pass autogenously on our equipment. So how does that compare? So if we compare the electron beam welding process to gas tungsten arc welding and submerged arc welding, you'll see that the welding speed is the same as gas tungsten arc welding and a lot slower than submerged arc, but we are able to hit a much thicker section. So in this particular example, on the EPRI vessel we were manufacturing, we were producing a 160 millimeter thick weld, compared to laying down multiple passes with gas tungsten arc or submerged arc of 1.5 and 3. So you can see there for the gas tungsten arc, we had to complete the weld in 106 passes, and the submerged arc 54. So for these two techniques are quite commonly found in nuclear supply chain manufacturers at the moment, sort of supplying the current fleet, the fleet of reactors that are being built. These are the sort of accepted methods. So you can see that the opportunity to reduce the actual arc time is massive. You know, we are talking orders of magnitude potential improvement. In addition to that, it's a much more automatable process. You can pre-program pretty much all of it offline and then check. You don't need any additional or any filler wire, so it's quite easy to control. It's easier to control the chemistry of the resultant component. You don't need preheat or interpass temperature, so that's a saving there, and it's significantly faster. The drawbacks. So in terms of the fit up, so alignment of the components before welding is absolutely critical. If you don't get that right, then the process will not work. So it is not a particularly robust process in that terms. You do need highly accurate setups, which brings in some of the other things we mentioned earlier on metrology and digital twinning to make sure you have that. And full commitment. So what I mean by that is, so if you've got a submerged arc process that is multiple welds, you will put in some of those welds, those layers, those passes, inspect. If that inspection is fine, you will continue. If you find a problem, you will grind out what you've put in, take any defects out, and then re-weld. And so you've always got a recovery. With a single pass welding process, you're pretty much committed from when you turn the machine on, press the go button, to when the component comes out at the end. If the process does fail, then you are likely to scrap the component. And if you've waited 12 months for a forging to arrive, that is not an ideal scenario. So you have to have an extremely high level of confidence before you put the component in the chamber and press the start button. And the other big drawback that's not mentioned there, it's currently not accepted in the codes for nuclear plants. So, you know, if we were to build a nuclear pressure vessel this week, we would have to use some arc welding techniques, because that is what the customer would expect, and we know how to build a safety case around that. So the role for the nuclear AMRC really is to prove that this process is at least as safe and at least a higher quality as the traditional techniques, and we'll be doing that by performing multiple welds in multiple scenarios, and then using that data to build a code case with our partners EPRI in the States, and then hopefully use that to deploy it in the future for the nuclear industry. Yeah, so we do it in chamber, homogenized. So we by sort of homogenizing, quenching, and hardening the weld, we hope to achieve a microstructure at the end that is essentially indistinguishable from what the base material was at the start of the process. So in that bottom image there, it's very hard to make out where the weld, and under a microscope, we are hoping to achieve a microstructure in that area that is almost indistinguishable from the base material. And that would mean then that the quality and the strength, the properties of the material in that area will be as good, if not better, than the base material. So one of the other technologies within the EPRI program is the development of complex near-net shape components. So currently there is a global challenge to forging supply chains. So we are investigating this near-net shape process as a potential to lessen the challenge and burden on forging supply chains. And we're doing it by what we call hot isostatic pressing. So the metal that you see in the image starts life essentially as a powder. It gets loaded into a pattern, a can, which is essentially a pattern, lowered into a machine where it is heated to roughly 3/4 of its melting point and put under a high level of pressure. That combination there of pressure and temperature causes the the powder to diffusion bond into the shape of the pattern and give you the near net shape. So this is a 66% scale of the upper head on the reactor pressure vessel. It's 3¼ tons. And in the image below, you can see the level of complexity that you can sort of achieve. So the image on the left, that is the designed component, and on the right, that's the component as it comes out of the hip. So clearly, the next challenge will be relatively difficult machining in order to get it down to that final geometry and put in those holes on that head. So that's an area we're also investigating at the nuclear AMRC. On machine probing, it says probing, but by that I mean inspection really. So all machine tools, all large scale machine tools now, modern ones, come equipped with probing for checking the dimensional features on components. And typically that is used to give confidence to move to the next stage, or to give you confidence that what you're doing is correct and the component is in the right position. But we can't generally use that data as the actual inspection data for the component, because if the machine itself has got an error in it, then that error will be replicated in the inspection data. So we've got a range of programs looking at how we could essentially justify that machine data is correct. So what we've done on our machines, we've installed an external laser interferometer. So there is a number of laser emitters around the machine. The machine will collect a reflector and will then travel around the machine tool, and the interferometer here will compare the performance of the machine to what the machine itself thinks it's doing, and then it is able to overwrite the control system of the machine to make it a far more accurate system. That still doesn't give you traceability to the national standard, it just gives you a higher level of confidence. So we've got a number of programs at the moment looking at how we can generate traceable measurements of a machine, and one potential is to use things like external metrology systems again. So this is a hexagon based system and an Echelon laser tracer, two similar systems where we install additional metrology systems to give a fully independent traceable measurement within the machine tool environment. Similarly, we're working on a major program for automated welding inspection. So this is actually to support the sort of arc welding techniques where you need to inspect at regular intervals. This is a project funded by UK government through BAYS with the partners listed there. And the work in the current phase was to integrate multiple sensors in real time onto a welding platform, just analyze that data in real time, and then correlate what we're seeing in the data to defects that we're putting in the weld. So we deliberately put defects in and then make sure that we can check or make sure that that is visible in the data we are generating through the sensor technology. So we concluded phase one of this this summer, where we sort of integrated four sensors into an arc welding technology, and we were able to at least see where defect scenarios were occurring. So we're currently at the point probably where we get enough of a signal to say stop the process, and then we can go and investigate it further. Future aspects of the work will be to put some machine learning on top of that so that the system will see that a defect scenario is potentially unfolding, and then in real time alter the processes in order to eliminate that, or to ensure that that defect does not occur. And we're currently looking now to fund a larger piece of work to make this sort of commercially deployable through the partners, mainly Babcock Cavendish. So supercritical CO2, very quickly. So it's a little bit counterintuitive, I guess, in that we are on a huge drive to minimize the generation and release of CO2, but we actually use it as a replacement for oil-based lubricants in the machining process. So typically when you're machining large components, you flood them with a large volume of oil-based lubricant. The oil-based lubricant is potentially harmful to the operators, and it has an environmental impact itself if not disposed of properly, and is very expensive. So we're looking at using CO2 gas to replace that oil-based coolant. We've done a range of trials in a couple of materials of interest to us. So in 304, we're seeing typically sort of productivity or tool life improvements of between doubling or 300% improvements. The similar results in 508. It significantly improves the tool life. It sort of eliminates premature tool failure that we were seeing using oil-based coolant. We are doing a lot of work now to ensure it has no negative effect on the sort of surface integrity or the fatigue performance of the components. And initially, we're not seeing any detrimental effects. So as well as those productivity in terms of being able to machine much faster, machine much longer with potentially very expensive tooling, what we haven't factored in precisely at the moment is when the components come out of the CO2 process, they are almost perfectly clean. So that will remove the need for quite time-consuming cleanliness operations, cleaning operations that are quite a contributor to cost in the nuclear industry, in nuclear component manufacturing. And we've also got a modularization team. So this is a case study that was actually for a thermal hydraulic test rig. Essentially, the team have developed a modularization assessment process, a way of scoring and breaking down systems. They're developing some software that will take 1 and 2D schematics and drawings and automatically turn that into a 3D design of an operating system. We looked at an existing design for a hydraulic test rig that was designed to be constructed in a sort of what we call a stick build methodology, the sort of typical way of bringing the components together to site and assembling them. And we looked at how we could sort of optimize that. So if we were to then break that down, but actually build those modules in a factory off-site and then ship them in these sort of structures. All the quality assurance is through digital work instructions and in a digital twin. So we have various digital twins of these where designers in remote locations, which was very handy over the last 2 years, can sit and cooperate and in real time make design modifications to these components, and then we can bring in operators or installers to look at the digital twin and do this sort of training and planning. And we're able to simulate how those modules move from a supply chain company or various supply chain companies or dispersed across the UK or further afield, and do a discrete event simulation of them arriving at site and then optimize the sort of assembly process and order to ensure that it's done in as short a lead time as possible. So just some key thoughts to finish on. In my opinion, nuclear is reliable, can provide electricity and high temperature heat, sort of 24/7, really, regardless of location or conditions. It's clean, it's zero carbon emission at the point of actually generating the electricity, and the amount of CO2 that's generated in the construction and decommissioning when sort of amortized over the lifetime of the plant is very low and makes it one of the lowest carbon emitting electricity generation technologies we currently have at the moment. SMR and further afield advanced modular reactors has the potential to address some of the key nuclear challenges, so they can make the construction of nuclear plant significantly cheaper, I believe, and foreshorten the construction time. The fact that up to 80% of the components and the assemblies will be done within a factory setting gives us the ability to deploy advanced manufacturing techniques that will further unlock benefits in deploying these. And the time at the moment, we're really seeing an opportunity for the UK supply chain. There is will in the current government at the current time to invest heavily in the UK nuclear industry. Hopefully the Rolls-Royce SMR program will get the momentum it needs and continued support of the government, and that will give us a real opportunity to create a design and manufacturing construction nuclear industry for new nuclear build in the UK that we haven't really had for a generation or so, and the opportunity to broaden that and go for significant export opportunities. And really the focus, well, my focus, I guess, on developing manufacturing processes is really going to be on Industry 4 type applications. So how do we, I've talked about individual technology development programs. How do we really integrate all of those into a coherent offering where the design engineers, the manufacturing engineers, the plant operation engineers are all working off a single data set. The components are, as they are shipped out, are manufactured to the specifications of the drawing, but the as-built data travels with them in a digital methodology, and that is used to optimize the construction and the through life operation of the plant. So yeah, the digital thread, as we like to call it now, the digital twinning and digital thread in nuclear going forward will be the sort of focus, I believe, or will help bring together all the individual technology programs that we and others are currently looking at. So at that point, I'd just like to open it up to questions.
Thanks very much, David. That was very interesting. Just before I start on the questions, and currently I have about 15 or 16. Okay. We'll see whether we can get through them all. But just to let people know that the CPD certificates for this talk will be available. It's just that I just don't know quite at the moment where they'll be put. The IET is moving the local network websites onto a new platform. And currently our website is in read-only mode, which means that we can't upload anything. But hopefully when you go to the new website, there'll be some means of pointing you towards the continuing professional development certificates that you can download and add your name to. Okay. Oh, the number of questions has gone up alarmingly. Let's see where we can start. Well, certainly Bill Ashcroft asked, who has quite a background in the nuclear industry, is asking, is Wilfer B on the cards for SMR? Or it may be too early to tell, but.
Yeah, Welsh Government are quite keen to explore the opportunities to deploy an SMR at Wilfer, or equally Trasfynydd. Yeah, so the Welsh Government have had multiple conversations with Rolls-Royce and other vendors on, the potential to use existing sites. So I think when we do build a Rolls-Royce SMR, it is more than likely, well, it's more than likely to be on the coast actually. So Wilfer might not be. Yeah, it will. I believe it'll be what is currently an existing nuclear site. Because of the size of it, 470, it's sort of compatible with the power stations that have been decommissioned over recent years. So it wouldn't mean major changes to the sort of connections to the grid, which is quite handy.
Okay, we have two questions, one from Christopher Rothwell, another from Stephen Spedding, which are very similar, and it's about your comment that the waste from the nuclear process has largely been dealt with modern technology. Could you explain that a little more? Yeah, so
there is no doubt that even with the most advanced designs, we still generate nuclear waste that is incredibly hazardous. But I think to put it in context, a Gen 3 nuclear power station, so for a lifetime supply of electricity for a family, the waste generated by that would fit inside a Coke can. What we've done over the last sort of decades, I suppose, really, in sort of decommissioning Sellafield and supporting that, is develop highly safe methods for storing, treating and storing that nuclear waste. But there is no escaping the fact that essentially the long-term solution is burying it deep under the ground in the geological disposal facility. So the siting and construction of that, it still needs to be completed. We still haven't got a site. We've got a sort of mid-level maturity design for a GDF, but yeah, greatly improved compared to the reactors that were built in the 50s and 60s, but perhaps not solved. Perhaps it would be a better way of putting it.
Keith Creswell asked a question that's related to your comment a moment ago about Wilfer. He said that the existing AGRs and PWRs are based on the coast. Can SMRs be sited elsewhere?
Yeah, they can. So the Rolls-Royce SMR, the biggest component that will be shipped will be the reactor pressure vessel. It will be road and rail. Well, it will be road transportable. So there is no reason why it couldn't be at an inland site if you've got the sort of water reservoir there to deal with it. I think the general feeling at the moment is it'll be at a coastal location. Certainly the first of a kind will be at a coastal location, and almost certainly at an existing nuclear facility.
Right.
Again, that's me guessing more than anything I know, to be honest.
Okay, thanks. Colin Megson has referred to, I think, a comment. It's just gone. Where is it gone? No, there it is. From GE Hitachi, talking about I guess that's their design as being so much more advanced than the UK's design, and so is much more likely to be implemented.
Yeah, so I mean, by advanced, do they actually mean advanced technology, or do they mean mature? Certainly far more mature.
Mature, the PWRX 300.
Yeah. So that is, yeah, they're essentially using a smaller version of a BWR reactor, boiling water reactor. But what the route Rolls-Royce, for instance, have gone is the pressurized water reactor. And it's true that in terms of the sheer amount of hours that have been spent on the design, they're probably quite far behind currently. But because they've chosen PWR, there's a lot of pre-existing knowledge in the supply chain, in the design community on PWRs from the EDFs and the people, and they are extremely confident that with their engineering might that they can bring to it, that they can quite quickly get the design ready for the GDA process as is. And that's what this phase of funding is largely about for Rolls-Royce, is to get them through the GDA process. And they believe that they'll be able to sort of catch up on that fairly quickly through going down a proven route. And yeah, I take Hitachi's point, this is also a proven technology. But yeah, I believe with the correct government backing, then they'll be able to bridge that gap.
We have two questions, one from Victor and one from Thomas, that are really related to the fuel for SMRs, sort of with the assumption that they're enriched uranium or plutonium, but the question about the possible use of thorium.
No, we are a long way from my area now, so I would have to take that one away and come back to you.
Right, okay. There's a question from John McLean, which again is sort of related to the GE one. He's saying, how much would we be, if at all, dependent upon China within the supply chain for SMRs?
Yeah, so it's hard. With all these technologies, wherever the companies that will always make a commitment to the local government or the national government that they're trying to build it in, that they will use their supply chains. What we've seen with the gigawatt one, certainly at Hinkley, is the real valuable manufacturing is still performed in the pre-existing supply chain. So a lot of the major forgings and high-end components for Hinkley Point C will come out of France with lower value supply chain opportunities for the UK. So if we go with Rolls-Royce, we will be able to grow, I believe, an indigenous supply chain for that. If we go with one of the other country technologies, we will almost certainly be reliant to a certain degree on existing supply chains in those countries, but it would come down to how or what deals the government negotiated with those technology vendors. It is quite difficult to say how much we would be reliant upon pre-existing international supply chains, but yeah, certainly more so than we would be with a UK-based design.
Right. We have another question from Victor. This is quite a long one. I'll just read it out. How many small reactors are needed to replace each large-scale reactor? So potentially many more planning permissions are needed. There's serious but rather uninformed public opposition to having nuclear reactors in its backyard. So is government taking any action now in parallel with this encouragement of SMR development to encourage granting of planning permission? for SMRs?
Well, we're not quite at the point yet of getting to the planning permission point, but in terms of the question of public opinion, the Nuclear Industry Association, which is sort of a trade body, if you like, for the nuclear industry, have got a mandate to help inform and educate the UK public on the potential benefits of nuclear in general, not just small nuclear. In terms of needing many of them, Rolls-Royce believe they've hit the sweet spot of designing a reactor that can be transported or in assemblies by road and by sea, while still producing 470 megawatts of electricity. So that's broadly similar to some of the older power stations that were built in the UK and that are now decommissioned. Similar, for instance, to the Wilfer plant. So it will be not as many needed potentially as you might first think. And the reason that I believe they'll be built on existing nuclear supply chains is because in those regions, typically you have a public who are more comfortable with the idea of nuclear power stations because they've lived with it for decades in many cases, and it has provided job opportunities and economic growth in the areas, and they are now at risk of sort of losing that as they come offline. But yeah, there is, in terms of then going wider than that and developing it and putting it in places that aren't currently nuclear sites, there is a big public information piece, and that comes down largely to the Nuclear Industry Association, but also people like Rolls-Royce will play their part in it as well. They are a big, powerful communication machine, as well as an engineering giant. And ourselves, the Nuclear AMRC, we're a relatively small organisation, but we have quite a big reach, if you like, quite long tentacles. So we will play our part as well in trying to put out coherent, understandable information on both the pros and cons of nuclear power in general, and then the individual sort of designs that we're working on.
In a way, a slightly related question from Jim: what is the effect of multiple small nuclear plants on the terrorism risk?
Yes, that's so clearly that is one of the very key considerations in the design of any nuclear power plant. They are designed to withstand airstrike from airplanes, so that's been in place for quite some time, even predating the sort of New York attacks. So they are able to withstand that. But what I touched a little bit on the future of manufacturing development being very focused around digital. That will go hand in hand with the digital cybersecurity considerations, because I think a lot of people in the industry see the sort of emerging threat very much being cyber threat, and the ability to get into maybe not even the control panels of a nuclear power plant, but into facilities like myself, where I'm part of the University of Sheffield. We might potentially be seen as a sort of soft underbelly of the nuclear industry. So the cybersecurity, as going alongside the sort of physical security measures that need to be put in place, will be absolutely paramount in developing these. But yes, I guess the fact that we end up with more power plants than we would have gives more opportunities for terrorism. So it will need to be given the sort of commensurate level of thinking, if you like.
Going back more to the technology, John Jacobs asks, how much pressure vessel manufacturing is borrowed from nuclear submarine technology?
In terms of the actual reactor, well, Rolls-Royce have gone to great lengths to make sure that there's a firewall between the two technologies. So the design is very much separate to the design of the submarine technology. That, like I say, they for national security reasons, they've gone to great lengths to make sure that they are completely independent arms. But obviously they do have a history of making reactor pressure vessels, and so there are people with that knowledge. And to be honest, if you walked into a pressure vessel manufacturer now and one sort of 30 years ago, you wouldn't notice a huge amount of difference, apart from some of the visual management that is put in place now to help quality in process and help safety. They are put on great big machine tools, great big welding bays that haven't changed dramatically in several decades. What we're hoping to do now, like I say, with the digital things, is sort of put a bit more intelligence and a bit more process. So yeah, there are people working on the program who have experience of submarines, but they are very, very separate technologies.
Right. Thanks. two questions from Mike Waldridge. The first one really is about sort of energy policy, so I'll skip that one for the moment. Can you say more about magnetism being a drawback of electron beam welding?
Yes, so again, it's not really my area, but essentially that beam is controlled through magnetic deflection. If you have any residual magnetism in your component or in your fixturing or in the setup, that will affect the direction of the electron beam. So you need to be very careful and very confident that you don't have any magnetism that you don't know about or in the setup. Otherwise, it'll deflect the beam and will not be welding the component in the area you need it to be.
All right. And Marek P asked a sort of related question on electron beam welding. It asked, and it may have been on your slide, but certainly I didn't spot it, but what is the energy of the electron beam used for welding?
God, that's a number that I did have and has gone clean out of my head. Let me get back to you on that, the energy sort there.
Okay, thanks. And Bill Ashcroft asks, has the supply chain been fully involved in the journey? Do the commercial teams intend to have a competitive bid the works and impose NEC harsh terms to drive down the cost? He goes on, but I'll not read the rest.
So in terms of phase one of the Rolls-Royce nuclear endeavor, if you like, there's a number of supply chain companies in the phase one. Now in phase two, the Rolls-Royce a new company has been created called Rolls-Royce SMR, which is majority owned by Rolls-Royce with some private equity firms and some international investment. They will then place requirements on the supply chain, and the supply chain companies will respond in a commercial manner. From what we're seeing at the moment, there's nothing particularly harsh about those T's and C's. They are commercial arrangements. They're not using NEC at the moment, but in future phases where they actually come to construct at these plants, they probably will. And Rolls-Royce are expert at driving cost out of manufacture, whether that's in-house or in the supply chain, and they will sort of put incentives in to ensure that the supply chain company are developing and optimizing in order to further drive out cost as they progress. But what's particularly exciting, I believe, about the endeavour at the moment is that the manufacturing team in Rolls-Royce is almost as big as the design team. So they are genuinely developing the methods of manufacture in parallel to the design. So the design for manufacture is at the heart of everything they're doing, which should eliminate cost before we even get to the manufacturing stage by these components and assemblies being genuinely designed for manufacture.
Okay, thanks, Dave. We're getting fairly late now. Although we have still 27 questions in the list, I'll take just a couple more. Perhaps I'll try and...
If you capture them all and send them to me, yeah, and I'll try and feed them back to you over the next week or so.
Thanks very much. There's one from David George, and he's wondering how many reactor coolant loops are in the UK and also the Westinghouse SMR design.
So I'm not sure on Westinghouse, but there's 3 steam generators in the Rolls-Royce SMR.
All right, so he goes on to say that he guesses there's a degree of on-site welding of these loops once sections are delivered to site. That's
yeah. So
a third part, which is are there prospective UK coolant pump motor and seal package manufacturers lined up?
So there are. We've actually worked with a reactor coolant pump company recently who are looking to ensure that their product range is suitable for various SMR technologies. So there are companies. Again, it's an area where we need to grow the supply chain. In terms of on-site welding, yeah, there will be some on-site welding. It's almost inevitable. The plan is to minimise that as far as possible. And then a concept that BAM Nuttall developed in phase 1 is what they call the site factory. So the first thing that will be constructed at site is actually a factory that goes over the entire reactor construction. And that will give you environmental control. So it'll almost be like performing welding in a factory. And there are a number of programs that TWI are looking at into how those on-site processes can be automated or mechanized as far as possible as well to get some of the factory benefits deployed for on-site welding.
Okay. Right, thanks, Dave. I think we've given you a hefty job there in terms of answering questions. So as we said a moment ago, I'll try and get all these questions out of the system and send them to you. And if you would be kind enough to try and answer them or find answers, then we can find some way of posting those, making them available to our audience. And just as a comment, there are a lot of people on the chat said thanking you and saying how very interesting they found the presentation.
No, thank you for having me. I've enjoyed it.
Good. So thank you very much again. As I may not have mentioned to people that this has been recorded, and once we're able to upload things to our site, our website, we will be making the talk available as a video on that, and we'll see what we can do about questions. So thank you again, David, for a fascinating talk, and we'll hope that we'll hear a lot more about SMRs in the not too distant future.
Thank you. Yeah, hope we do.
Thank you everyone for attending. I noticed that the audience, it was about 196 at the beginning, and at the end it was 196. So I'm hoping people found that really, really interesting. So thank you to everyone for attending, and thank you again, Dave.
No problem. Thank you.
Right, good night.
Yeah, cheers.